so far, we've been looking at the stresses that a material is subject to based upon some kind of loading. These are internal stresses we're talking about. For the most part, we're assuming that they're constant, or we're dealing with the average values. It's not necessarily true, but it certainly suffices for the problems we're doing. Part of why it works is because even if we look at the true distribution of stress internal of some kind of solid, we treat it as an average, which means in certain places we're overestimating the stress, certain places we're underestimating the stress. But then when these things go to design anyway, a factor of safety is applied. Which is generally calculated as something like the maximum anticipated load, and this can be on the forces themselves, it could be on the stresses that result from those forces. Remember that even though the forces through a member may not change, the cross-sectional area may change, which causes the stress to change. The maximum load over the design load. In other words, once you've calculated what the maximum loads are, and again, we may take this as an average value, which means we're a little bit worried that we're underestimating the stress at certain places. We apply this factor of safety, which takes us way over the top. So if we're calculating for these average stresses, we apply a factor of safety, which can be somewhere on the order of 2, 3, 4, 5, depending upon what the application is, where you figure out what the maximum load is, and then you simply design for twice that. So you're well over the maximum that we were missing because we were averaging. So we eliminate the concern. It also eliminates uncertainties. There's uncertainties in tests, uncertainties in manufacture. It's certainly possible you get some corrupted material from the manufacturer. It doesn't have quite the strength it is advertised to have. Very high factor of safety when the possibility of failure could be more catastrophic than some other situation, which may mean greater loss of life, but it could also mean that the whatever machine part does fail could be more catastrophic to the rest of the machine than some other less crucial part where you could apply a lower factor of safety. Because generally, the higher the factor of safety, the more the cost. Because you're going to have to put in more material to increase the area, or you're going to have to put in more members to decrease the force in each of the members for the area of which you design. We'll work with we'll do a couple problems with those if it hasn't already come up. I'm not sure in the problems as we go through these. I don't want mine to go off. All right, so we've come up with some stresses. We've got two types here so far. The normal stresses due to axial loads and the shear stresses due to transverse loads. And by axial and transverse, I mean the direction of the forces causing the stress, the orientation of those forces to the area that's absorbing that force. Normal stresses are always perpendicular to the cross-sectional area used to calculate the stress. Shear stresses are parallel along the area that are absorbing that stress. All right, so that's nothing we couldn't have done in statics. There's nothing there that has anything really to do with the strength of materials. We very easily could have calculated all that in statics. But now we're going to add to it a little bit and start looking at the actual result of these forces on these members. And we'll see that as what we call strain. And again, there's going to be two types of strain. We'll have a normal strain and we'll have a shear strain. And I'll work up both of those now. As a material, as a member is loaded, we know now that of concern is not just the load on it, but also its cross-sectional area. The greater the cross-sectional area, the less the stress, and without even knowing anything in the particulars of what happens to materials, the lower the stress, the better. So we know that for some given cross-sectional area, and one of the typical ways we do it in engineering is we, in the member itself, draw what the cross-sectional area looks like as if we've cut through there and then turned that area on its side so we can see it. That's one of the ways that we demonstrate what the cross-sectional area looks like. If it was a square member, you might draw that. If it was a triangular member, they'd all look the same on the side, but they look very different when we just draw the little sketch that shows what the cross-sectional area is. Often that's entirely sufficient to then actually calculate that area as you need. So whatever the cross-sectional area is, as of yet we are not worried about what the shape is, we're just worried about what the area is. We'll find out very shortly how the shape of that area plays into it. We can have beams with the very same area and they're going to act very, very differently under loads, as we'll see. So we know that if we've got some member with some cross-sectional area under some load, that we could figure out the stresses in that piece. What we haven't looked at yet is the response of the member to those loads, other than to say if the loads are too great, or the area is too little, or the combination of the two in ratio. The stresses are too great, the piece could fail. What the piece will do before it fails, however, is actually elongate by some measure. And let's say by an amount del. The normal strain in an elastic solid, and though it may not necessarily seem like it, structural pieces made of iron, steel, wood, all of these pieces are somewhat elastic. They will deform a certain amount. If you don't deform them past a certain limit, then when you release the load, they will return to their original size. Of course, you can imagine with steel and the like, this deformation is very, very small, but with certain other structural materials like rubber, which can be used in certain structural situations, as we'll see, this deformation is large enough to even be visible. So our symbol is eta. The lower script, sorry, that may be sigma, I'm not sure. Epsilon. There we go. Epsilon. Yeah, that sounds better, thank you. You speak Greek. Our definition of the normal strain, epsilon, is simply that amount of elastic deformation divided by the original length of the piece. Simple as that. Load a piece, measure how much it deformed, you can calculate then the normal strain on the piece. What are the units? The units come in about 12 different flavors, whatever you want, because it could be meters per meter, millimeters per millimeter, or you can look at the units as if they simply cancel and there are no units at all. The strain could be just simply a pure number with no units. However, this deformation is generally very, very, very small compared to the original length, so it's quite likely that the strain values will be on the order of something like 10 to the minus 6th meters per meter of original length. And of course, same for inches. And of course, the units do disappear if you so wish. We can also call this amount deformation of 10 to the minus 6th units per original unit length. We might call a micro. Sometimes just left it like that. Remember that scientific notation, sorry, the SI prefix notation of this is 10 to the minus 6th. So sometimes it's as micro, actually they wouldn't do an M there because that implies that there are still units. It's not uncommon, and I believe our book does it, actually puts it in, and it calls it a radian. Remember, radians are sort of mystical units that come and go when needed, and so that's one place where they're just thrown in. Remember, the radian came from a ratio of lengths itself. It's also possible that you could list it as a percentage, where it's the percent of deformation to original length. So in there you'd have to, of course, multiply the calculated value by 100.
If it was in compression, would it be a negative number?
Sorry?
If it was in compression, would it be a negative number?
Exactly, right, yes. And that's important because strain in one direction is very different from strain in another direction. Some materials are very, very different in their reaction to compression than they are into tension. That's precisely true. It's also true that if we have a solid that's twice as long with the same area and the same original load, that the deformation will be twice what it was in the first one I showed. By the way, let's put the load on there. So this now would be a deformation of twice what it was before. And you can think of these elastic solids very much like springs, especially a linear spring. In a certain region, this response is linear. we'll see shortly more specifically what happens. If we have back to the original length now with twice the load, we can expect twice the deformation compared to that original picture. So we have those possibilities plus any other combinations thereof. Just what this deformation comes out to be, of course, depends upon what the solid is itself as well, what material this is. Steel is very different than would be if this piece we were talking about was rubber of some kind. So we're going to relate the material properties itself to this response in the next day or two. Might hit it Friday. All right, to exercise that a little bit, let's try a problem. Imagine we have a simply pinned beam of some kind, supported by two rods, one about here, and these are also pinned, and then one a little bit farther out, and a little bit longer. All right, the dimensions. All of these dimensions are in meters. So 2 there, 1.5 there, 2.5 meters across there, 2.7, and then another ½ meter on the end, because it's the end where we're going to apply the load. And some load P is there at the end. Now, for our purposes here, so far, we're going to assume that this beam, the horizontal beam there, is what we call a rigid beam, meaning it itself is not going to deflect under any loads. It shouldn't be too much a stretch of your imagination to imagine if we loaded a beam in that way that it's going to deflect due to those loads, maybe something like that. We're going to assume, with the rigid beam assumption, that there is no deflection like that in this beam. It's not accurate, of course, because the beam will deflect like that, but that's something we hit much nearer the end of the class. In the last month of the semester, we'll look at the deflection sideways of beams to transverse loads like this. So, rigid beam, no deflection under the load applied. However, with what we're doing so far, what will happen as this rigid beam is loaded these two members will absorb that load, and because of the natural strain, the normal strain in those members, they will elongate. So the beam may not deflect itself, but it will rotate a little bit about that one pinned end. Due to the stretch, if you will, in the supporting members. All right, so we want to figure out something about what that is and get used to the numbers given. All right, we'll call this support 1. This is support 2. And we're given that the strain in 2, the normal strain in 2, is something like 800 micrograms. Now, right now, we don't have the capability of calculating that beforehand, as we would in a design situation, where we would imagine we're faced with this scenario, and we predict, based upon what the materials are, what this strain will be. But it's something that's very easily measured because it's nothing more than the geometry of the situation. If we built this up, loaded it, we'd simply measure the increase in distance from the top of support 2 to where it now currently is. So what we're given is the information of what this deformation is in piece 2. Just simply measured it. So our task then is to find the strain in that first piece. What does it suggest? Well, one thing we can always do, start with the definition. We know that the strain is going to come from however much the piece 1 deforms compared to its original length. Piece 2, or piece 1, sorry, is back here somewhere. So we know it's going to deform an amount like that. If we can determine what this amount is, we can use similar triangles to determine what that amount is, and then simply calculate the strain. How does this help us find that, which will give us that, which will give us that? Very, very geometric problem. This, of course, is the deformation of 2 divided by its original length. So take a second or two, calculate those up. Even though with strain the units do cancel, you still have to get the relative size of these numbers correct. So this is a deflection of 800 micrometers per meter of original length. Which I believe is almost a millimeter for original length, original meter length. Is that right? 1, 2, 3 for the decimal place, and then 1, 2, 3 for the milli prefix. So that piece is originally almost 3 meters long. It's going to deflect over 2 millimeters, which may be enough to make this, whatever this piece really is, not work in its original intended purpose. If we were storing bowling balls on this, they might not stay. If you go into the bowling ball storage business. Anybody have that deflection?
2.16.
Oh, okay.
Yeah, that's what I have. Not that.
I thought it was, at the moment there, I thought it was the strain, but I forgot. So
Yeah, that's just the deformation.
That's a measurement of one.
Which came from the strain. Yeah, and that's purely a geometric measurement. If this was actually a test piece, you would simply measure that. Well, maybe not simply. You can need a micrometer stand of some kind, I assume, but we have one in the physics lab. From that, by similar triangles, you can figure out what the deformation of one is, and then from that you can find out what the strain is. So strain is a very, very geometric problem, as it will remain so when we look now at, after this, at shear strain. Exactly the way that springs act, linear springs act. And we'll put that together in exactly that form, possibly on Friday, maybe not till Monday. What do we have for the deformation of the first support member? Phil, you have that?
I got 0.96.
0.96 millimeters?
Millimeters, yeah.
Agreed? Yeah. By similar triangles. That, again, is based upon the assumption that the beam itself is undergoing no sideways deflection. There's no axial deformation in the beam, just merely a rotational displacement about the pinned end. And then we include the fact that the original length was 1.5 millimeters. And so, how did you express your answer then? Remember, there were several choices for ways in which we'd express this strain, it being generally a very small number.
Well, the first strain was expressed in microradians.
Generally is a good idea. You put it back into the units that started the problem. If there's not a request to the contrary, that works as well as anything. And so how many then microradians is the strain in piece 1?
640.
Two. It's what?
640.
640. How about as a percent? can express it however you wish. Generally, on tests, I'll put the way I want it expressed. Just makes grading easier if I don't have to convert your answer to some other set. This expressed not as microradian or micro, 640 micros, but as a percent. Just make sure, just a little practice, making sure. We're going to have a lot of things we have to do where we very carefully have to watch how many powers of 10 we have in these problems, which is the same thing as where is the decimal point. As we get to other numbers, these are very small numbers. Some of the stresses are very, very big numbers. When we put the two together, we get even greater extremes. So, Tom, Joe, either one of you have this as a percent? Not yet? John, you all right?
Just trying to tack up.
Travis, would you pass your coffee forward, please?
So much left.
Just grounds. You'll take it. Who's got it for me? Of course, David. Chris, you do too. Did you check with each other? Travis? Phil, you got it? As a percent. A millimeter is 10 to the minus 3 meters. That's going to divide to 0.64 times 10 to the minus 3. And how many percent is that? Somebody save me here.
0.064%.
David, confirm that. Chris? Very, very small. Very, very small numbers. And we're going to find that with when we put strain and stress together, that's actually going to cause a little bit of trouble for us as we actually go to visually demonstrate the response of these materials to the load and the stress that's in the piece itself. All right, same thing here. However, what if, as this thing is put together, there's going to be manufacturing tolerances. What if, as these things are put together, there's a 1 millimeter gap in the pin connection on piece 2? Is that going to change things? Then what is the strain in the piece 1? Is that going to change things in any way? Assume that it still has the same strain in it, though.
What does that mean? I can move a millimeter before it's...
Yeah, there's a little bit of slop in the pin connection in this, such that as this load causes the beam to move, to rotate a little bit, it'll move a millimeter at this connection before there's even contact, full contact in the piece. just manufacturing tolerances, or possibly a certain size pin was planned for but not actually available, or a combination of the both. How does that change things? So that the connection at 2 is going to drop by that amount, but what is that amount now? Such that it still has the same strain in it. If that's the strain, that should lead us to the actual elongation of that piece. What is that elongation? If that's the strain, which was the same strain we found before, what now is this actual elongation of piece 2?
Oh, wait, you added a double. I don't need it.
This comes directly from the strain. The strain's the same as it was before, so should this be the same as it was before? It sure should, because it only comes from one place. This number hasn't changed, that number hasn't changed, then that number's not going to change either. So the actual elongation of the piece 2 is the same. What, however, is the deflection of the connection point?
1 millimeter more.
1 millimeter more, because it's going to move to take up the slot, then it's going to start straining this piece up to the strain we found in the first place. So maybe we'll call this capital Del, which will be Del 2. So this will be Del 2 there. Capital Delta 2 equals Del 2 plus 1 millimeter. And so that changes things back here, so you're going to have to find a delta 1. But again, now it's similar triangles as it was before. This is del 1 plus some unknown amount, just simply due to the greater deflection down here. Well, actually, that's not quite right, is it? Because there is no slop in this piece down here. So, so this will be del 1 itself, since there's no slop in that connection. So, by similar triangles, what, John?
A slot both of them. What is
There probably will be slop in both of them, just by the nature of physical connections. You know, the more precisely things are built, the more expensive they are to build, so depending upon what this application is, it may actually have quite a bit of slop in it. What's this then, the deflection here? We know this to be 3.16 millimeters, so this is, it was 0.96, is it going to be greater than that? Yeah, because it's a larger triangle, if nothing else. believe it's 1.4 millimeters, sound about right? And then now the strain in this piece is that 1.4 millimeters over, I can't remember, the original length of the piece unstrained. And how many microrads is that? Get that number, we'll take a quick break, reset the tapers.
933.
David, you agree? Depending on just how much round off you took through this problem, something like that, 930, 940. Remember, there's a big factor of safety in these things anyway, so the last significant figure or two is not going to be of great concern. You're going to design way over that limit anyway. All right, stop tape for a bit. All right, again, we're getting our first chance here to look at the actual response, the physical response of these materials, these elastic medium, to the loads being applied to them. We just looked at the normal strain, defined as the amount it deflects under load divided by the original length. Purely a geometric problem. So we'll add to that now the shear, the response of the materials into shear, also as a physical deformation of the solid. So if we have either some structural solid or some elemental piece thereof, subject to some kind of shear load, and we looked at how on a cubical piece like this, these shears must be the same magnitude all around and oriented in somewhat that fashion. We looked at that on Friday. What we didn't look on Friday is what the response of the material is to those type of loads. Again, I've arbitrarily chosen which direction these all lie in. I could have easily picked the other way. But a piece under that kind of load will start out as a square shape, and then, given what I showed here, will deflect to something like that, where that end there we might call del again. That was fairly useful. If we had coordinate directions on this, which we often do in these pieces, we would call this then del x, possibly, just to highlight the fact that there are going to be other strains in other directions. And that, as shouldn't be a surprise, is also some function of the original length. We define then the shear strain as the change in angle of some original angle. In this case, it happened to be originally 90 degrees. It now undergoes a change to whatever that angle is, depending upon the geometry. And we'll label this gamma xy. Xy meaning this is the piece, our view of this piece is in the xy direction, xy plane. So, in this case then, the shear strain in the xy plane for that little picture is defined as the original angle, 90 degrees, or pi over 2, because this is generally done in radians, minus whatever the current angle is. So the piece, that corner angle started out at 90 degrees. It's now some deformed value, theta prime. I'm not exactly sure why it's got to be theta prime. Why couldn't it be just theta? But that's some of the tradition of this area. And so we get now a change in the angle of that much. As shown, this is a positive shear strain if the piece was such that the angle grew to be greater than 90 degrees. As this one over here happened to do, that would be a negative shear strain. And again, it's a purely geometric problem. That's, by the way, the average shear strain. Locally, we can get different shear strains. If you imagine a rigid plate on top of a deformable solid, like a piece of rubber, and this, by the way, when we have this type of thing that absorbs some kind of transverse loads in it by deforming elastically, is called a shear block. These are very common at the ends of bridges to absorb the thermal expansion of the bridge itself with temperature change. You can imagine in an area like New York, for example, if you go down near exit 14 and putting a new bridge across the Northway there. They're doing it in relatively cold weather. In August, it could well be over 100 degrees. That bridge is going to get substantially larger. By substantially, I mean we could see the change. It'd be visible to the eye. And this rubber block can absorb that. The thing is, it will probably deflect more like that rather than like this, which means that the shear strain is a little bit different at different places along here. If we actually had a grid drawn on here, we'd see that that grid, if it was made up of squares, would have different shapes at different places. In that case, then, the local shear strain, the non-average shear strain, sort of like instantaneous deflection, would be the local deflection divided by the local distance there. In other words, just the slope of the shape of the piece itself now.
Is the whole block rubber, or just the top little portion?
These are rigid plates.
Okay, I didn't hear that.
As what well, the reason I want these to be rigid plates
It makes sense.
is because I don't want them to elongate, which adds a different dimension here. The strain on this side would be different than the strain on this side if the plate itself changed length, which would be a normal strain. In real life, that indeed happens. However, again, for these kind of applications, generally the deflection in the support plates is substantially less than the deflection in the elastomer, the rubber-like solid that's absorbing that movement. All right, so if we have a deflection due to shear loads like that, we might actually get a response of the piece to become something like that, highly exaggerated and not to scale.
That's supposed to be a parallelogram.
Why, it doesn't look like one? This is in all the things I have to draw, especially in this class. You're learning already, I hope. This is a very graphical class. It depends a lot on your ability to draw pieces. This is one of the hardest things to draw, because those faces don't stay parallel to their original location. Is that better?
Yeah.
That's an awful lot better. Anyway, half of the strain is there, half of the strain is over there. They may not be the same, depending upon what the piece is itself. This is a positive strain. And if instead of getting narrower, it got fatter. Gee whiz, this is hard. So now we're deflecting that way. That's an example of negative strain. Yeah, look at your book for drawings done by the graphic artists that they hire. By the way, that's part of why these books get to be very, very expensive. All these drawings are done not by the author, they're done by graphic artists they hire to do each one of them in considerable detail. All right, so let's this again, not only is it entirely a geometric response, a deformation of the piece determined purely by the geometry before and after, but it can be actually measured in that way. You can go to a piece and scribe on it a square and then look at the deformation of that square due to the loading. It's got to be enough that it's measurable. It might not be. But it's purely the geometric response of the solid. So as an example, let's start with a simple plate. 720 millimeters on one side, 480 on the other. In original, unstressed, unstrained dimensions. And again, this could be a particular part of the, whatever it is, a machine of some kind, or a support plate of some kind, or it could be an actual inscription on the piece itself. Let's say it deflects to something like this. Again, not necessarily to scale. And that deflection here is 0.5 millimeter. And the deflection here is 1/4 millimeter. Find then the strains at the two places. So we'll call that one 1, that strain deflection 1, and that 2. Because the total, sorry, wrong symbol. Gamma 1 and gamma 2. Because the total of those is those two things added together. Because remember, the original 90-degree corner here, the total change in that angle is the strain, the shear strain. And then the two of those added together. is the total shear strain. So we have an original 90-degree angle down here. And the change in that angle is the shear strain, the total shear strain, which is the two of those added together. Again, rather simple calculation, purely geometric, but has to do with some numbers of rather different sizes. This deflection of one end is much smaller than the original, than the length of that side transverse to that. Plus, don't forget, you have to get the signs right, if any. So how'd you find gamma 1? Anybody have it? This is, by the way, the Greek letter gamma.
In radius.
It can be an either, but if the straight calculation, if you use these numbers here, it will be in radians automatically. You can convert it to degrees, but typically it's given as in radians or unitless as well. It can have the same type of numbers, same type of presentation that did the normal strain. How'd you find gamma 1? This shear strain in the first location.
R10 of 0.5 over 720.
Actually, no, we just take the original. The original numbers. These are very, very small angles,
Doesn't matter.
right? So that's why we don't need to take the tangent of them, because the tangent of a very, very small number is the same as the number itself.
And that's also why you didn't use that method when you showed us the differential means of
Yeah.
showing strain.
Yep. You can, if you see it better that way, you can take the tangents, but. And then this is over the original pieces itself. Of course, it's driver nuts with those tapes. Comes out to be give it to me in radians, microradians, and percent. And for some of these, since they're very, very small, you have to carry enough significant figures through the problem, and then round it off at the end generally. How many radians is that? David, you ready?
.001215.
001215. How many microradians is that? That stands for 10 to the minus 6, so move it over 6 places. 12, 15 microradians. How much percent is that? This one's millimeters per meter already, just move it over 2. So it could be less than, just over 0.1% deflection. So again, very small numbers, but numbers that may be enough of concern that they can't be ignored. Depends again on the situation. All right, any questions before I clear up? This, as much as anything, is just simply a matter of trying to wade through the geometry of the problem, seeing what is deformed and what hasn't. Find a 90-degree angle that's deformed. Find what it's changed to. All right, so a wrap-up problem. Some kind of structural member under some load. 12 kilonewtons. Original length 500 millimeters. Original diameter 16 millimeters. Due to the load, this piece will get substantially longer. Well, I don't know if substantially, that's a relative term. But because the density is the same and the volume is the same, then not only will it get longer, but it will get narrower as well. Not all the way back to here. It'll spread out to the original connection distance, but remember we're looking at average strains here. So let's say it increased in length by 300 micrometers. So not very much, barely visible. And now the change in diameter so I'll call that del D. Del, remember, is our symbol for change in length due to this loading. Is 2.4 millimeters. So if that's our X direction, that's our Y direction, that's our Z, we need to find the normal strain in the X direction and the normal strain in the Y and Z directions. Since it's circular, those two will be the same anyway. Maybe we can just call it the strain in the radial direction. All right, we'll double check that on Friday, because that's the end of class.